Kia ora and welcome to today's webinar. Today Linda's flying solo as Sam is away sick, but we couldn't delay because this is really important information for us to share with the many users of SMAP prior to the scheduled update later this month. Linda is a principal spatial data scientist at Manaaki Whenua and has led the modelling and data management that sits behind the SMAP system since its inception. She will outline the changes, the science behind the changes, and the impacts of the revisions on water storage information. I'll be back at the end to help with your questions, so don't forget to put them in the chat box as soon as you can. Now over to you, Linda.
Christine, kia ora. Just before we dive into the water retention information, we just have a quick discussion around how SMAP coverage has been expanding. And so MPI and 12 regional councils have co-funded the expansion of SMAP coverage over the last, well, for 5 years. And for the last 4 years, we have added 1.45 million hectares of new mapping, and a further 1 million hectares is due for completion by August 2025. And that's indicated by the dark orange on the map. And so some of that is coming through this coming August, and the rest of it will be available in the August next year. Overall, we've now added about 7,000 different siblings or soil types have been identified within the SMAP. It's the reference sites. Now, reference sites are critical because they provide the information that we use to estimate the water retention for all SMAP siblings. Sites with lab measurements of soil retention are costly. So this is where someone will go into the field, take samples, send them off to a laboratory where they're analysed, and that is $10,000 per site for the water retention information in particular. That's quite expensive. When between 2014 and 2020, we have doubled the sites. We added 371, that effectively doubled the data set. And then since 2020, we've added a further 112 sites. So if you do the math on that, that's an investment of $1.1 million. The funding for this soil water retention research has largely come from the SMAP NextGen MB Endeavour research program, which is now finished. Some of it came from the Critical Pathways MB program, and MPI and the councils have also contributed. Some of you may have seen this slide, but it's worth having a little look at what the SMAP information system is, because most of you will be seeing that top level, the delivery level. SMAP Online, where we do the maps and the fact sheets. That's our public-facing, public good website where we make all our information available. We also have the LRIS portal, which is where we supply the GIS data. This is to, some of it's publicly available, and some of it is licensed. We supply information to third parties for use in their systems. Sometimes it's just internal, and other times it might be public-facing. And finally, we have the web feature service, which is how we supply SMAP data to OverseerFM. And so they will make a request within Overseer, comes across to our database with a request, what's the information for this location? We send the information back in real time, and then they populate Overseer with it. That's what's called a web feature service. So all of that delivery is underpinned by the information inference engine. And this in turn is supported by the underlying data, both the spatial data and the morphology that's collected by the podologists when they're out in the field, the reference site data, which I just talked about, which is where we have laboratory data, and it is stored in the National Soils Data Repository, the NSDR for short. That's the analytical data. And of course, we also draw upon general soil research into development of soils and how soils respond to management. Let's take a little bit more of an in-depth look at that inference engine. There are the three inputs, the soil survey data, the reference data, and the general research. Because soil data the knowledge comes in many shapes and forms. We have the sensor data or the lab data. We have expert knowledge. We have heritage data, legacy data, both in the form of data and also research papers. We have models. Sometimes they're in the shape of rule-based models, statistical models. Statistical models there, rule-based ones there, and then mechanistic type models up here. The inference engine is making sense of all of this information, integrating it, codifying it into what we call pedo transfer functions. That's the PTF, pedo transfer functions, PTF for short. So we can't measure every soil. So the pedo transfer function allows us to predict information for those many soils that we cannot measure. And that's the power of SMAP. It means that the updates to the base data are automatically processed into soil information. We can easily update it with new knowledge, new models, new experimental findings, and everything is documented. We know where any given estimate has come from. The whole thing results in a really flexible, dynamic soil information system by which we can provide consistent information. So looking a little bit more specifically at the soil water retention pedo transfer function in particular, it is a statistical model. And so there we have the data from the NSDR database, which is all of that laboratory analytical data that's been stored. We need to extract that, plus we need to extract all of the data which is cheap to measure, that we have lots of information on, because that's what we use to do the extrapolation. So we look at those cheap properties, cheaply measured properties, and the expensive ones like soil water retention, and we do some statistical modelling. It's an iterative process, and eventually we test it, we split it into a training and validation, and eventually we come up with a model that we're comfortable with, a good prediction. And then at that point, we can extrapolate out to all of those siblings where we only have the cheaply measured properties, and we can extrapolate and get these more expensive, the estimates of the more expensive properties. That's the extrapolation part of it. So now let's talk about the new model, the 2024 model we call it, what the update involves and what some of the implications of that are. Soil water retention is the capacity of a soil to retain water. So over here on this graph, this is what we call saturation or total porosity, when the soil is full of water, so much so that gravity is pulling out some of that water. After a while, it'll reach, within a few days, it'll reach a state of field capacity. And this is where the water is being held within the soil so that the plants can uptake it through evapotranspiration. Once they've done that for a while and all that water starts to disappear into the upwards, then the pores will have no more water in them. They're full of air. Now there is still water at this point, but it's so tightly bound that the plants can't extract it. So it's not available to the plants. But at that point, we call it wilting point. If we look at the next graph, you can see here there's the wilting point, for example, and it varies with the different texture classes. So the wilting point in the sand is quite low. This is the water content here compared to a clay soil. And that's why soil texture is quite a good predictor of these key points in the water retention, like wilting point and field capacity. There's field capacity, and the difference between the two is what we call available water. It's available to the plants to extract and to grow with. And you can see that there is less available water at the sand level than there is at the silty and the clay soils. So this available water is a really important number for production purposes. How will the crops grow? For irrigation demand, how much more water is needed by the soil for the plants, and nutrient losses. Because if the available water is not very big, then water can be lost, and that might take the nitrate with it. So in terms of the additional data, since the last update of the water retention in 2020, it is a mix of new data, legacy data sources. We've done quite a bit more QA. So looking first at the soil orders that I've put in gold there. So the allophanic, that has increased a number of sites from 42 to 64. Now, at each location, we take a number of samples. So we might take one at the top of the profile, and a bit further down, in different depths, we're taking maybe 4 or 5 samples at any given location. So that's what the end column is in terms of the total number of samples. So those the allophanic soils have near doubled the number of samples that we now have, which is good. The granular soils, we had very, very few sites for that. At least we've nearly doubled that. And again, we have nearly doubled the number of samples that we have for granular, but it's still very low. Pumice is another one that we have focused on. So we've got an increase there of the number of sites and nearly 50% more samples for the pumice soils. Now this column down through the middle, that indicates the coverage in SMAP of each soil order. So the higher the number, the more representative that particular soil order is of New Zealand soils. So looking at those, the allophanics at 1.1, they had 554 now, but it only had 264. That was why we really focused on the allophanics. We needed to get that number up because it covers such an important part, a big part of New Zealand, particularly in the Waikato area. Going down to the mature pallets, 743, that's a pretty good number, representative number of samples. Non-allophanic browns, 841, that's great. 1.2 pumices. Now you can see now that's why we really needed to increase the pumices, and there's still room to collect more. The recents at 691 are pretty good. All these other ones with very small numbers have really quite small areas of that soil order in New Zealand. So the model from 2020 is based on a research paper that we did in 2018. This one here, a geoderma paper. We have now written a new paper explaining our new model, which has just been submitted. Hopefully it will be published within a month or so. And this describes the statistical modelling that we've done to predict those key properties on the soil water retention curve, the wilting point, the field capacity, the total porosity that I mentioned earlier, and from which we can derive properties like available water and macroporosity. Let's look at some differences between the two key models. The 2021, it's a beta regression as described in that paper. The new one is a generalized additive model, GAM regression with a better response, and as I said, just been submitted. With the 2020 model, we had very little data for the organic horizons, and so we just used a default value for all of them. Whereas now we've got a bit more data for the organic horizons. It means that we do now have a specific model, so we get a range of values for the organic horizons. The number of sites I've already talked about, and the number means we have more samples to train the model with and more to validate it with. We're now doing a 70-30 split, where we keep 30% of them to one side to validate the model. Overall, the increase in number of samples is 28% increase, but that's focused particularly in some orders, and those orders that we really wanted to increase, it's mostly by 40 to 50% increase, which is great. But there are still some that are a bit low in terms of the numbers of sites and samples. 2020, there was an improvement in the goodness of fit metrics. So that tells us whether a model is a better fit to the data or not. And we've got an incremental improvement, further improvement in those goodness of fit metrics with the 2024 model. The error model from 2020, we weren't really able to use that. It had some issues, whereas now we have an error model. This means that rather than just doing a mean estimate or prediction, we can start bounding it or giving an interval of the 90% confidence of when that value falls within. So we can start to get an idea of the uncertainty of any given estimate. And I want to put some of that information onto SMAP Online. The big difference really between the two models is around the robustness for the extrapolation. So, for example, we had 4 sibling horizons in SMAP that could not be predicted under the old model. It was too unreliable. Whereas now, all sibling horizons can be predicted with our model. To make some additional assumptions in order to cope with that insufficient data under the 2020 model, we still need to make some assumptions, but only 2 are now required. Raw soils, we treat them as recent. We have no data for raw soils, but essentially they're very similar to the recent or clay for some particular types of raw soils. So we're quite comfortable with that assumption. And the second assumption is that the high clay pumices, again, we don't have any data for them. We treat them as brown soils. We think that they will behave more similarly to a brown soil than the more sandy pumices. And again, we're reasonably comfortable with that because we have been doing a field study in parallel with this modelling work, where we have taken some measurements of water content out in the field on some pumice soils, and we find that the data is more consistent with the new model than with the old. Here we have some pretty plots. It's broken up by the different soil order. What it's showing here is the green dots are the estimates across all siblings under the 2024 model, the new model, whereas the orange dots are the points under the 2020 model. So it shows the difference between the 2020 estimates and the 2024 estimates across all siblings. The black points are the measured data. That's the laboratory data. And that the obvious thing that kind of jumps out when you look at these plots is they're quite variable. There's quite a range there in some of those values. There's quite a spread in those black dots. And that's what makes the modelling quite difficult, is having that spread. Another one to point out is the mature pallets. And here's an example of all our data, the measured data is up here. So silt's along the bottom and available water on the y-axis. So where there's quite a bit of silt in the soil for the mature pallets, lots of data, but where the silt is low, we don't have any data. And so what the model's doing is it's using the other soil orders to get a sense of what the prediction should be. And you can see that there's quite a bit of spread there in the orange, the old model, whereas now it's tightened up and it's the new predictions there in the green. The granulars, remember them, they had hardly any sites at all. So what we had to do with them in 2020 is we had to assume that they were like a different soil order, which wasn't wonderful. As you can see here, the brown, the orangey dots, those are the predictions according to silt, where we were assuming that they were like melanics. Now we treat them as granulars. We've got enough data. The model's reasonably well behaved. You can see there with the green predictions, they're a reasonable match to the black measured dots. Pumices, this one was interesting. So you can see there's quite a tight, a sharp gradient under the orange, the 2020 model, in response to silt. It's quite steep, and that's kind of at odds with all of the other orders. Whereas now, with the new model, the green, it's a bit sort of flatter, it's a bit smoother, it's a bit more consistent with some of the others. And as I said, that field study that we did over the last year is confirming that the green values are a better match than the orange ones. Right, just looking at a quick summary of change across the orders. So the box here is showing the median change in available water, the profile available water, down to a depth of 60 centimetres. And so the allophanic ones have gone down, a decrease of 4.7 millimetres only. Brown, I'm just going to go through the ones with the high areas. The brown have gone up, increase by 7.7 millimetres, pallets by 7. A bit more of a change there. The pumices have increased by 21.2 millimetres, the recents by 8. And here you can see a little bit more of the variation because it's just the median value. Looking at those allophanics, you can see here, so the box plot shows you 50% of the values are within the box, 25% below. So here the graph is 0 through the middle there. So anything that's below the 0 is a decrease, anything above is an increase in the value of available water to 60 centimetres. And here you can see that nearly 75% of the allophanics are decreasing. All of the granulars have decreased. The organics, remember, those are the ones where it used to be a single default value. Now there's a model, and some of them have gone up, and some of them have gone down, and there's quite a bit of variation there. Pumices mostly increased. There are a few down there where they have decreased, but mostly it's an increase. And these ones are all very close to that zero line, not much change. So looking at it spatially, the colour scheme here is that light green colour, pale green. That is with a change of plus or minus 5 millimetres. A very small change in the available water to the top 60 centimetres. The next one up is the light blue, which is a change, an increase of 5 to 20 millimetres. You can see a lot of the North Island falls into that. Some of it falls into the 20 to 40 millimetre increase. The brown, the yellowy red colours show a decrease. You can see there's a bit of a decrease happening over here in Taranaki, and also these isolated red ones through here, which are probably the granular soils, they're decreased. Now the granular soils have got very high PAW to start with, so a decrease of 20, 30 is actually not going to make a lot of difference to those soils. South Island's a much more muted picture over there. They're that light green colour mostly. It's either very little change or in that 5 to 20 millimetre increase. Done a couple of analyses of the impact of this change. The Overseer very kindly tested the impact on about 6,500 farms, and they took the data from 2020, the data from the 2024 model, ran it through and looked at the difference in the in-loss budget from each of those farms, with the result that a third of them have actually got no change at all. Vast majority of farms, being those two rows, will have a slight change of a decrease in the in-loss per hectare of up to 10% decrease. 5.7 of the farms up here will see an increase in their in-loss. 58% of farms will have a decrease in their in-loss. Now, just be aware that Overseer will not be auto-updating the soil values for all of the farms. Any new request that is made as of a couple of weeks' time will get the new data for the SMAP soil moisture properties, but there won't be an update. There'll be a button whereby the values can be updated, but that will be for the users to do. And then we have an IRICalc impact analysis. This is where we have, this is John Bright from Aqualink, kindly did an analysis, 8 different locations, the soils within 1 kilometre of the 8 locations. The axis here is the y-axis is the change in PAW. So for a decrease of 30%, there will be an increase in the water demand, as you'd expect, of only up to 10%. Vice versa over here, with an increase in the PAW, then there will be a decrease, negative numbers, decrease in their water demand. Again, only up to 10% in most cases, one out there at 17% decrease in the amount of water demand. So that's hopefully given you a summary. In terms of the release date, we are aiming for the 23rd of April. The SMAP is science driven, so there is change from time to time. But our goal is always to provide the best information that we can for farm management and for environmental outcomes. There has been a really significant investment in the reference site measurements over the last decade. And the new model is mostly improved in its robustness and our ability to extrapolate across all these siblings. It's a national scale model, so it does mean that all soil moisture data values will change when we make this change in later in April. And finally, just an acknowledgement, MB for funding much of the research behind this update, MPI and the regional councils, and of course the farmers for allowing us on their land to take our samples and do our observations of the soil properties. Thank you. Over to you, Christine.
Thanks, Linda. That was great. I certainly learned a lot about how it all works behind the scenes. Quick question first, though. How often is SMAP updated?
Yes, good question. Look, we aim to do an update every August of every year, but sometimes there are reasons why we might do additional updates. So we did one in December last year, and we're now doing this one in April. It's not doing any new coverage, it's purely an update of the water retention models. And the reason for doing it in April and not waiting till August is because the councils were keen to get this new information in place as soon as possible.
Thanks for that. It's good to know that we can be flexible when the demand is there. Now we've got a couple of really interesting questions. One, you might need to go back to slide 9, but Darren asked us why the number of immature gley samples has gone down. It went down from 196 to 148. Was that a reclassification?
No, it was good spotting. So what I didn't explicitly say, but there's just a little thing in there of QA, and we did a lot more rigorous checking on some of the data, and for various reasons we had to drop some of those gley ones, and that's why they've gone down, because they weren't, the numbers, the training data wasn't up to scratch, or there were problems with it, and we had to drop those from the training data.
And it was the same with oxidic?
The acidic, well, there's no increase there, so still 8 sites. Oh, and we've gone down, yeah. So we've lost a couple of samples. Yeah, same thing. Yeah.
Right. Good to know the QA system is working as well.
Yeah.
Now,
it's always
Bill
disappointing
has asked,
when we lose data.
Exactly. We can't afford to do that too often.
No.
Here's a maybe tricky one. How much do farm owners use SMAP?
Oh, cool. So every now and then we do a survey of all SMAP online users, and the information we get from that survey, I can't remember the numbers, it's a few years since we've done it, but farmers are very heavy users of SMAP. And anecdotally, I'm always getting information of how people are using SMAP to understand the soils on their farm. Obviously, Overseer is a big aspect, people using SMAP, feeding it into their Overseer budgets, but a very wide use by farms or by farm consultants who are then advising the farms. It was something like 50–60% of our users were farmers or farm consultants.
Great. And one last question. One of our plant and food colleagues has asked whether there are any mechanisms for measurements from other organisations who are also measuring soil characteristics in their various projects to contribute that data into the development of SMAP.
We would love to have access to that data. Please come and talk to me.
Now that is a great place to end. I don't think we've got a couple of other questions come through. Rest assured, we will be in touch with you with responses, and those along with the presentation from today and the recording will appear on our website so that you can access it and share it with others forever. So I'd like to say a big thank you to Linda. That was a great presentation. If you have further questions, don't hesitate to get in touch. Join us again next month. We'll be back again and the details will be in your inbox. Ka kite.